and I got cut off on the last slide. But essentially, we're running this coevolutionary arms race with antimicrobial drugs. So Fleming discovered penicillin. Penicillin became used in the 1940s. We know that it was widely used during World War II and continued to use penicillin to treat all kinds of infections through essentially the 1980s and early 90s. So you might stop and ask yourself, did we know in 1940 or 50 that penicillin was only good for the treatment of gram-positive bacteria? Probably not. Okay. For antivirals or for our viruses, it used to be, and I remember this in the 1980s, even 90s, early 2000s, a child could go to the pediatrician with an ear infection. They are not going to extract the fluid from behind the tympanic membrane to do culture and sensitivity. Because you poke that tympanic membrane with a needle, then essentially you're creating one area of that tympanic membrane that's not going to work anymore. So you might have had ear tubes. The more times that you have ear tubes inserted, the more hearing loss that you acquire. Okay, so putting a needle into the tympanic membrane to pull out fluid in the ear is not a way to diagnose most childhood ear infections. So essentially, sometimes, many times, antibacterials were given for a viral ear infection. Most ear infections are, in fact, viral. So there was a lot of misuse, overuse. Patients also misused by not completing their round of antibiotics, by not following the instructions, by skipping doses, by stopping too soon. And all these things can lead to essentially inadequate killing of those microorganisms. So then we have some persisting that are resistant to the medication that was used to fight them off to begin with. So let's take a look. So there's a couple of different ways that microbes become newly resistant to a drug. And so one of those is spontaneous mutations in what we call critical chromosomal genes. That's going to be related to the key feature that we're trying to target with our antimicrobials. And then the second way is acquisition of entire new genes or sets of genes through what we call horizontal transfer from another species. So this goes back into viral reproduction, which we learned about early in the semester. So let's have a little review here. Okay. Let me see what I need to say about this. This is just more about thinking about natural selection and drug resistance. But essentially, if you have a microorganism that has an adaptive response, so it's tolerating a medication, then it's going to not work as well. So it can tolerate a certain amount of that drug would normally be inhibitory, but now you have to use more of the medication maybe to be effective, or it's outright immune to that particular antimicrobial. The second bullet point, due to the genetic versatility and adaptability of microbial populations, then they develop this drug resistance. So that's what we're about to talk about, spontaneous mutations, and then, of course, the acquisition of new genetic material through horizontal transfer. So the last one can be intrinsic. So that just means me, myself, and I, as I'm replicating, it's just to my strain, if you will, or to my lineage of cells, but you can also acquire that resistance through horizontal transfer, and you can also acquire that through what we call conjugation, which is the closest thing we have to bacterial sex. All right, so resistance factors. So remember how our bacterial cells have their own DNA. But they also can have these circular pieces of extra DNA called plasmids. So these plasmids can actually contain some resistance factor. And so you can get that from other nearby bacteria, just giving that over to you or donating that to you. So that's a problem, because maybe my cell is completely susceptible to penicillin or amoxicillin or whatever it is. But once I get this resistance factor from a plasmid, now it doesn't work on me anymore. So that's how that works. So resistance factors, as I mentioned a moment ago, it can be transferred through bacterial sex, we call conjugation. And there's a couple of other words there I'm not worried about you knowing, but essentially just knowing it's a way that bacteria can freeload or freely donate, I guess, plasmids to each other. So they can share that resistance, those resistance genes, and so this makes it harder in a population to essentially reduce the population, because now a particular bacterial population may have some immunity, so they have some resistance already. Okay, a nice little graphic from your textbook. So when we think about natural selection, we think about this figure of 1, 2, 3. So let's take a look. So 1 tells us, okay, so we have a lot of bacteria. You have an overgrowth of bacteria, maybe in your sinuses. Maybe it's a virulent form of staphylococcus. So you have all this drainage, you have a lot of pressure in your face. Maybe you have a fever, some postnasal drip, just a lot of gunk in your face. So we start to give you an antibiotic, and you can see in the figure number 2, the antibiotics are killing all the bacteria causing the disease or the illness that you have. And it turns out, yeah, they can also kill some good bacteria. So that's why we want to do culture and sensitivity and know in those more serious infections, usually requiring hospitalization, that we're giving that person the right antibiotic. So we really want to be using a narrow spectrum antibiotic, so we'll make sure we're not just killing off the good bacteria. So in the panel number 3, we will have some of those bacteria that were making you sick. They're showing us here, these red bacillus. They're the larger ones. You see how there's different sizes. But essentially, it's showing us that these are the drug-resistant bacteria, and now they're dividing by binary fission, making copies of each other, and now the population is overgrown with this drug-resistant variety. So they're allowed to grow and take over. So you may go back to the doctor and go, hey, I'm not feeling much better, or I was getting better, but now I'm feeling worse. In which case, maybe the antibiotic, or maybe your infection has some of these resistant strains. So then you would need to get a different antibiotic. Now here it shows us in the last panel this idea that you can give horizontal transfer. So one bacterium can essentially give a plasmid to another bacterium and say, hey, I have this resistance factor on my plasmid, I'm giving it to you, and now you have that resistance. So we do have a bit of a concern, I'm just going to end on this, of running, again, this co-evolutionary arms race with bacteria, and we may be entering what we call a post-antibiotic era, where some infections will not be treatable, and I'm going to say by business as usual. So new and effective antibiotics have been slow to come to the market. And if it were me, I would always be careful about taking antibiotics and making sure you're really needing it, and that it's not a viral infection or something else that can take its course. But essentially, we are using many different tactics, chemical warfare, if you will, on these antibiotic resistant infections.